Hello everybody and welcome to another GCSE Chemistry question walkthrough. What we're going to be doing is looking at exam questions from the chemical analysis topic, and as ever what I recommend you do while you're watching this is pause the screen when the questions first appear, and then as I go through my reasoning and the chemistry behind what's going on, I will write down my thoughts behind the question in blue, and then you can see exactly what you need to write to get your answers because I will write the answers in green. Okay, this first question is about mixtures and pure substances. And so diving in on the first question, we are asked which of these substances are mixtures, and they have told us that there are two, and we've been told to tick two boxes, so make sure you follow instructions like that by keeping track of the number of marks and the number of ticks you've been asked to put in. So in terms of the thinking behind this, we've got air, carbon dioxide, graphite, sodium chloride and steel. Now carbon dioxide and sodium chloride, those are compounds, and we know they're compounds because when we write their formula we're writing two capital letters for both of them, so they've each got two elements inside them. And speaking of elements, graphite is made of the element carbon, and so that is not a mixture, which means that our two mixtures must be air, which is nitrogen and oxygen mostly, and steel, which is iron and a number of different substances that get added to make stainless steel or high carbon steel. So carbon is obviously something that gets added to steel quite typically. And then moving on to the next question, we've been asked to connect lines from pure substance in chemistry and pure substance in everyday life to 5 meanings on the right hand side. Now some of those meanings are meaningful but not relevant, but the two that we need to connect up for this: a pure substance in chemistry is a single element or a single compound, so emphasis on single there. Only one type of particle is present, whereas a pure substance in everyday life is, like pure water that you might drink. It's a substance that's had nothing to add to it. You might say in everyday life, but a chemist would think that pure water was only water. Now, two of the last three statements in the meaning section actually do have meaning. So a substance made by mixing substances in precise proportions is a formulation. So that is a decoy option from this topic, in fact. So anything from shampoo, toothpaste to emulsion paint, those are formulations because they are mixtures with very precise fixed proportions. And similarly in the sort of separating mixture ballpark with filtration, which is where you remove an insoluble solid from a liquid. And the only one really that doesn't have any meaning is the middle one, a substance containing only atoms which have different numbers of protons. So this final one is a decoy because if we change the word different to the same, then what we're describing is elements. And so elements might be confused for being pure. So that's a decoy. It doesn't actually have any meaning as it is written like that. And then these final parts to the question are about testing for gases and testing for ions. So we here are testing for chlorine gas, and they've got 4 tests. And what's a little bit sneaky here is that actually they're all 4 legitimate tests that you need to know about. So a glowing splint relighting, that is the test for oxygen, and a lighted splint giving a pop is the test for hydrogen. Damp litmus paper turning white, that actually is the test for chlorine. And then lime water turning milky is the test for carbon dioxide. So you need to know all 4 of these tests, but obviously it's the damp litmus answer. And then a student tested a metal chloride solution with sodium hydroxide. A brown precipitate formed. What was the metal ion in the metal chloride solution? So again, you need to know all 4 of these precipitate colours. So precipitate is an insoluble solid that forms when you mix 2 solutions together. And calcium is white, so it's not that one. Copper is blue, so it's not that one. Iron 2 is green. Sometimes it's described as a dirty green, which means it's not that one, which means the last one that forms the brown precipitate is iron 3+. And there are two other white precipitates that you need to know, and they are aluminium 3+ and magnesium 2+. And both aluminium and magnesium give a white precipitate as well, but then the subtlety about the aluminium is if you use an excess of sodium hydroxide, then the aluminium precipitate will dissolve in the presence of excess sodium hydroxide. So that's how you can differentiate between calcium, magnesium and aluminium. You can pick out the aluminium like so. This next question is about paper chromatography, so that's part of the required practical from the chemical analysis topic, and so they're describing how the chromatography is being carried out. So somebody's putting a spot of food colouring, X, here is X, on a piece of paper, and then they're putting 4 separate dyes A, B, C and D next to them on a start line here, and then they're placing the paper into the water, here is the water, and then what's going to happen is the water will, well, they've not told us what's going to happen, but we know that the water will rise up the paper and these different substances will dissolve in the water and rise up as the water does, and they'll rise up different distances. At least that's what's meant to happen, because it's not going to happen because the student who's been doing this has made 2 mistakes. And they are all visible from the diagram on this occasion. Sometimes you have to read the text to find out their mistake. The first mistake is that the start line has been drawn in ink. And so what would happen is the ink would run up the paper as the water moves up. So we've been asked to explain, by the way, so that's why I've gone into more detail than just pointing out the mistakes. So we've been asked to write down the mistakes, but also explain why that would cause a problem. And then the second mistake, also from the picture, is we've got the water, as we know, at the bottom, but what you can see is that the level of the water here is above the start line for the samples. And so as a result of that, the food colourings that are A, B, C, D and X, they wouldn't necessarily rise up the paper, they would dissolve into the water and we'd end up with just coloured water and it just completely wouldn't have worked. Okay, this next part of the question goes on to say that another student has done this experiment and they've done it properly and it has worked. And so on the diagram what you can see is we've got the solvent front, and the solvent front is how far the solvent, in this case the water, has risen up the paper. So it's risen nearly all the way up to the top. So that's how far the solvent got. And then we can see that substance A got this distance, maybe about a third of the way, B went nearly up to the top, etc. And we can also see actually on the right hand side that substance X has got 3 substances in, and we know that because they have all travelled different distances up the paper, so that we can see that X has got 3 things in their mixture. And so we've been asked first of all to calculate the RF value of dye A. Now the RF value, just for your background knowledge, is a number between 0 and 1, where 1 means it's travelled up to the top of the solvent, so it's travelled all the way with the solvent, and 0 means it has not moved. Now you calculate the RF value by doing the distance travelled by our sample divided by the distance travelled by the solvent, and that's how you get a value between 0 and 1. If it's not moved, then the number on the top is going to be 0. If it's moved all the way with the solvent, both of those numbers are going to be the same, and so we're going to get 1. So that's how we get 0 and 1. So on this occasion, the numbers will depend on what size screen you're watching this on. I hadn't realised this when I was planning the question, that people's numbers would be different. The good news is, once you have calculated your RF values, they will be the same as mine, even if your measurements are slightly different. So, how do we get these measurements? First of all, we're talking about dye A, so we need to find dye A and draw a small line halfway through dye A, like so. And then, starting on the start line, we draw an arrow up to it and we measure what that distance is. Now, for me, that is 1.9 centimetres, so the distance travelled by my substance is 1.9. And then we need to find out how far the solvent has travelled. So again, starting on the start line, we need to go all the way up to where the solvent front is. That's where the solvent finished. And measuring that, I got 4.1 centimetres. And so we've got 1.9 divided by 4.1, and that gets me an answer of 0.46. And so that would be my final answer. My RF value would be 0.46. Now, you should have something that's similar to that, but depending on what your measurements were, you will be allowed some flexibility either side. So I would suggest that anything from 0.43 to 0.49 is probably okay. Certainly when you've been doing this off a screen it is, but just make sure you're making careful measurements, and I'm sure you'll get this RF value correct. And then the next question goes on to talk about dye D, and it tells us what the RF value is for dye D. There is no spots shown on the diagram, so that will be because they're asking us to work out the distance moved by dye D, and if it was given on the diagram, you could just measure it. But what they want you to do is they want you to use the same equation as before. RF value is substance divided by solvent distance. And so when we put these numbers in, 0.8 is equal to our unknown divided by the distance our solvent travelled, which is 4.1. It's the same as before, and we've already measured it up here. And so the calculation then becomes 0.8 multiplied by 4.1 is equal to our unknown. And when you crunch those numbers, you get 3.3 centimetres. The other way that you can think about this is if the RF value is 0.8, then that means that the solvent has travelled 100% of the distance and our substance has travelled 80% of the distance, because 0.8 is 80% of 1. And so what you're effectively doing is you're saying, right, well, if my substance travelled 80% of 4.1 centimetres, well, they must have travelled 3.3 centimetres. And you can do that, kind of as a shortcut and not having to plug the numbers into this equation, or you can have it as a sort of a reasonableness check, because an RF value of 0.8 means it's gone 80% of the distance, and 3.3 does seem reasonable, doesn't it, as being 80% of 4.1. And then the final question asks us to explain how the different dyes in X are separated. We've already said that it's a mixture of different substances. This is quite a nice question for 4 marks, really, because we can pick them up without using very many words. So, as we've already said, the solvent rises up the paper, and you'll get a mark for saying that. And then these different dyes in X will have different solubilities in that solvent. So solubility means how well does it dissolve in that solvent. And not only that, the different parts of the mixture will have different attractions for the paper. And so as a result of this, they'll have different attractions to the paper and the solvent, and so they will travel different distances up that paper. You could also use the word mobile phase instead of solvent if you fancied mixing it up and making it even sound more technical. And you could use the word stationary phase instead of paper, but you don't have to use those terms, because what this really is, this is a kind of a tug of war between the solvent and the paper. And if the solvent's got a really strong attraction to a component, then it will travel a long way up the paper. But if the paper has got a really strong attraction for the substance, then it won't travel so far. It will travel this short distance here. So we can say that this substance at the bottom, whatever that is, has got a really good attraction for the paper and not for the solvent. And this one at the top has got a really strong attraction for the solvent and not the paper. Then the question goes on to take a look at flame emission spectroscopy. Now, for most courses, this is only on triple science, and so that means you might not need this if you're doing combined science. But how you approach this question is a bit like how you would approach a chromatography question, because we've got our display for our mixture at the bottom here, and then we've got our 5 different metals that the mixture could be made up from. And so what we have to do in the flame emission spectroscopy is we look for clusters of lines that are present in our sample, and we look for matches, so for telltale lines that you only find in one place and not in others. So for instance, as we track upwards, we can see that we've got this common line between sodium and our mixture. And we've also got this cluster at the bottom like this that looks like it's a combination between sodium's lines and calcium's lines. And so what this tells me is that this is a mixture of calcium ions and sodium ions. And you could write the name or the formula. And then we've been asked to explain why a flame test could not be used to identify these two metals in the mixture. And this is 2 marks, so we need to go into detail. So first of all, calcium and sodium's flames, whilst they're not identical, they are similar. And so these colours would probably mix together or they would mask each other. And that's all you need to write for these marks. You could go into detail about what the colours are for sodium, which is yellow, and orange-red for calcium. That's absolutely fine, but you don't actually need to here. And I think if you do that, you run the risk of kind of misremembering one of the colours and then therefore losing the mark. Okay, so the last few questions are about testing for ions. And starting with this one, we've got an unknown compound X, and we've been told some facts about X. So they've added water to it, and it didn't dissolve. They've added a solution of ethanoic acid to it, and it produces a gas which turned lime water milky. And as we've already said, that's carbon dioxide that turns lime water milky. And the chemical that produces carbon dioxide is a carbonate when you react them with acid. So acid plus metal carbonate will produce carbon dioxide. And so the students have made some claims. One student says that it is sodium carbonate and the other says it is copper chloride. Which student, if any, was correct? Now, the answer is they're both kind of correct, but they're incorrect, both of them. But they're both partially right. So in terms of student A, they are correct that this substance is a carbonate, but we're actually going to get our marks here for saying what's wrong with what they've said. So the sodium carbonate is wrong. Sodium carbonate would not be green for a start, it would be white, and sodium carbonate does dissolve, whereas this compound X doesn't. So that's 2 reasons why student A is not correct, and we get a mark for each of these bullet points. And then for our 3rd and 4th mark, we need to look at student B. So student B is saying copper chloride. Well, it can't be chloride, as we've already said, because the chloride would not give us our fizzing with then the lime water turning white. So student B is incorrect because adding acid to a carbonate produces carbon dioxide. So carbonate must be present rather than the chloride ions. Okay, this next question is more of the same sort of chemistry, but it's been displayed differently. It's been displayed in a table where we've got 3 compounds, X, Y, and Z, and 4 tests have been carried out to identify what the ions are in these compounds, and you have to use these results to work out what ions are present. And a really important command here is you have to identify the 2 ions that are present in X, Y, and Z, and you're only getting 3 marks in total, which means you need to get both of the ions correct in order to get the individual marks for each of the compounds. So if we just take each kind of test at a time, I think. So if we look at the flame test first of all, flame test is a test for metal ions, metal positive ions, and then we've got nothing for X, and we've got nothing for Z, so we've not learnt anything here, but the yellow flame, that is proof that it is sodium that is present in the yellow flame. And so we can say that Y contains sodium ions. Now, if we move on to the next test, we can see that sodium hydroxides, that's also a test for metal plus ions. We've got no reaction for Y, but that's fine, we've already identified the sodium. The green precipitate and the brown precipitate, those are 2 positive results that are both for iron. The green precipitate is iron 2+, and the brown precipitate is iron 3+. You could write the formula, by the way, you could write Fe 3+ and 2+ if you preferred. You don't have to write the formula, you could just go with the name. And so moving on, the adding hydrochloric acid and barium chloride solution, that is a test for sulfate ions. And no reaction, we've not learnt anything there. The white precipitate for X tells us that we have got sulfate ions present. So what that means is that X is iron 2 sulfate. Sulfate is SO42 minus, but the names are absolutely fine because they've just told us to identify the ions, nothing more than that. And then last of all, nitric acid followed by silver nitrate. That is a test for the halide ions, which sometimes written as X minus, but that's any ions from group 7. So no reaction, but that's to be expected because we've got sulfate, not one of the halide ions. And so we've got yellow and we've got cream precipitate. So that is 2 positive results. And just watch how you write this. This is iodide for Y, not iodine. Really important. You'll be penalised if you write iodine. So iodide, which is I minus. And then for the cream precipitate, that is bromide, or Br minus. Again, we need the IDE. When the group 7 elements are ions, they are IDE. And if you chose to, you could, instead of naming the ions, you could actually name the whole thing, and you could call X iron 2 sulfate, Y would be sodium iodide, and Z would be iron 3 bromide. But just naming the individual ions is absolutely fine. This final question is again presenting you with some test results. We've been told what has been done to this eggshell sample. First of all, hydrochloric acid was added. We know that that is a test for carbonates. A flame test was done. We know that that is a test for the positive metal ions. And the sodium hydroxide, we know that that is a test for the positive metal ion as well. And test 4, we know that that is a test for the group 7 ions because we've just seen those in the previous question. So the student concluded that the eggshell contained carbonate ions. We agree with that because a gas is produced in test 1. Describe how the student could identify the gas produced. Well, we've explored this already. They would use lime water, and lime water would go cloudy if carbonate ions were present. You would need to say just that for the 2 marks. Then part 2, the student concluded that the eggshell contained aluminium ions. Do we think that the student was correct? Well, there's 2 reasons actually why they are incorrect. So first of all, the flame turned red during the flame test, and that tells us that calcium or lithium is present, but categorically aluminium would not give us a flame colour. So that is the first piece of evidence that they are wrong. And then the second piece of evidence that they are wrong is that we got a white precipitate that formed that did not dissolve. So it did not dissolve, which means that aluminium can't be present because aluminium's hydroxide precipitate dissolves when you add an excess of sodium hydroxide. When you throw bucket loads of sodium hydroxide in, that precipitate dissolves, whereas this one did not. And so the fact that you get a red flame and a white precipitate tells me, in fact, that calcium must be present in order to give those 2 positive results. And then the student concluded that the eggshell contained chloride ions. Is the student correct? Use their results to justify. Well, they got a white precipitate when they did the silver nitrate test. So it seems that, yes, chloride ions are present. But what's really quite intricate here is that they did the silver nitrate test on the colourless solution that was left over from test 1. And test 1 had been acidified, not with nitric acid, which is typical for a silver nitrate test, but with the dilute hydrochloric acid. So even though we did get the positive result for the chloride ion in the silver nitrate test, hydrochloric acid contains chloride ions. So we actually can't be conclusive here, which is why there's no right answer in terms of the yes or no mark. We have got some evidence that there's chloride ions present, but we can't say that they came from the eggshell when they were definitely present in the hydrochloric acid. So that's a tricky question, which ultimately is inconclusive. And then the final question, we've got scientists wanting to investigate the amount of lead found in eggshells. They used a modern instrumental method, which was more sensitive than older methods. So instrumental methods just means like using a machine. Name one instrumental method for identifying elements. Well, flame emission spectroscopy is the instrumental method that you need to know about. So that's all we need to say to get our 1 mark. And then what is the meaning of more sensitive? Well, you've got a few options here. Ultimately, more sensitive means that you can detect smaller amounts of a substance than doing a flame test, for instance. You need far more chemical on your flame test nichrome wire than you do in your flame emission spectroscopy. Or you could say that it allows you to use a smaller sample size. That's another alternative answer for this question. Okay, that's the end of these questions. I hope that was useful. I'll see you again soon.